Everyone, welcome back everyone who was also here last week to the morning session, first day of this workshop. So it's my great pleasure to introduce our first speaker today, who's David Ridout, who's beaming in from Melbourne, Australia. He's going to talk to us about exploring higher rank logarithmic vertex operator algebras. So thank you very much, David.
Thanks very much, Jethro. It's an absolute pleasure to be beaming in as it is. So a very good evening to you all. And I just really wish that I could have been there, but unfortunately it wasn't to be. So, thanks to all the organisers for putting this on under such difficult circumstances over the last, year or more of trying to get things up and running. So very appreciative. Today I just wanted to report on some relatively recent work with a whole bunch of other people. So Rajan Thomas, my PhD student Zach, Kazuya, Thomas's former PhD student Matt Rupert, and Simon Wood. Possibly I may have forgotten a few people, my apologies to them. And it's basically centered on what we can say about the detailed structure of the representations of higher rank logarithmic POAs. And the answer is, of course, that we're still very much a work in progress, and the results are fairly limited, but we've developed some techniques which are, I think, interesting. So, without further ado, I'm going to try here to mostly tell just a story and not get bogged down on details or try to introduce too much nasty notation. There'll be a little bit of that just to sort of set the scene. But the basic idea is really to try to just give a flavour and a high level overview, something like that. So please do stop and ask questions whenever you feel like it. I'm more concerned with making sense than I am with telling a story with a finale. So I'll start with a little bit of motivation, which is purely personal, and review a tiny bit of history. So those are two pretty short sections. Then I want to talk about what I'm calling a rank 1 story. And so this is going to be basically we're going to be looking at certain logarithmic vertex operator algebras related to SL2. So we'll be looking at the affine case as a archetypal example. And then the new results, the interesting stuff, should be in the fourth section about rank 2 logarithmic vertex operator algebras. And here I'm talking about SL3. So I think there will be a little bit of overlap with Dražan's talk tomorrow, but I've tried hard to make sure that I don't say too much, which is in detail. So you'll see when we get there, assuming we do get there. All right. So my motivation is representation theory. That's kind of what I end up doing most of my days. So as you probably know, I think I can. Okay. I was hoping that Zoom would be able to pick up some sort of cursor here, but you can see that's not really working. Apparently I can just do that. Oh, well. So we have various types of vertex operator algebras, and the ones that we meet in textbooks are, of course, often the easiest ones to understand. And so in sort of one corner, we have rational vertex operator algebras. And here I'm using the original definition in physics. So rational here means that we have a finite number of irreducibles up to isomorphism, and the category is semi-simple. So here we've got, our favorite lattice POAs, but we've also got things like fermionic, free fermions and ghosts, and minimal models galore, and even a few W-algebras. So there's, lots of examples. You could write a very long textbook about all of these examples. And then there are sort of non-rational versions, which I've got here in the top right corner. And so here I'm thinking, that's going to really bug me. Bit acrobat. There we've got things like the free boson. So that's not a particularly difficult VOA to understand. And then there's sort of other things which may be non-rational, but maybe not. We're not entirely sure. Things like Liouville and Western-Witten models relating to non-compact target spaces, all sorts of possibilities there. I would describe both of these as being factorizable, which probably doesn't mean what it means in some parts of mathematics. All I mean by that is that when you write down the state space of the corresponding conformal field theory as a representation of the tensor product of two copies of your VOA, then it decomposes direct sum of irreducibles. So that's sort of as nice as it can possibly be, and that's what we're sort of brought up, at least in physics, to assume always happens. Okay, and so down towards the bottom row, we have what I'd rather refer to as logarithmic VOAs, and so these are vertex operator algebras in which the module category is not semi-simple. And more to the point, what we expect is that somewhere the Virasoro zero mode L0 is going to have a Jordan block of non-trivial rank, so at least rank 2. So these are called logarithmic VOAs, and we can sort of have log rational VOAs in which the spectrum is discrete. We have a finite number of irreducibles up to isomorphism. And then, of course, we have the maximally difficult case, which is probably, almost surely, the generic case where our vertex operator algebra is not only logarithmic, but also has a continuous spectrum. And so there we expect to have not only a non-semi-simple category of modules, but also an infinite number of irreducibles. And so, on the discrete side, we've got our good friends symplectic fermions and triplet models. And there's probably some other examples, but there aren't so many that we know for sure. You can build them sort of out of things like parafermion models and so forth. But there's not too many examples of the log rational guys. In physics, there's sort of this hint that some of the theories describing things like polymers and percolation might be log rational. But I think we're still very far from knowing if that's the case. If it is the case, then it seems quite plausible that the VOAs corresponding to the Schramm-Lohner evolution models might also be log rational. Again, too early to say. All right, but I'm interested in the more sort of generic case, so logarithmic with a continuous spectrum. And here I'm thinking of things like our bosonic ghosts, the Chiral algebra, or symplectic bosons if you prefer. Western-Witten models with supergroups often have this type of VOA. And then there's various others, and today I'll be talking mostly about what in physics are called fractional level Western-Witten models, which in math, of course, are affine vertex operator algebras at fractional levels. So we'll be looking at admissible levels to make life easy. All right, as I said, ask questions if there's anything you need to ask. So you remember rational VOA. So again, I'm using physics nomenclature here. Basically, it means that the module category is semi-simple, so all our modules are completely reducible. There's only finitely many irreducibles up to isomorphism. And I'm going to come along and say, just to introduce terminology, which is probably not standard, I'm going to describe all of the modules of a rational VOA as being Q-finite, which just means that when you write down the character, which I've written here, but I guess you won't be able to see because of this. Okay, if I hover, you can probably just see that little dot. Yeah, they're the characters when we just write down in terms of Q, right? We don't introduce any additional variables to keep track of other weight spaces. Right? This already makes sense as a character. So we don't have infinite dimensional conformal weight spaces. Okay, and if we go to the log rational setting, we lose the semi-simplicity, but we keep these two finiteness conditions, which is nice. Okay, so where do I want to go? I want to break the C2 cofiniteness, and there's a very natural class, our sort of Lie theoretic VOAs, so affine ones, and certainly a large proportion of the related W-algebras, where you have weight 1 fields. So in most, although not all, but in most cases, what you're going to end up with then is something which is no longer C2 cofinite. You're going to have infinitely many irreducibles, and then you have to sort of figure out ways of keeping track of them all. So that's kind of the plan for today. And I want to start with some ancient history. So many people will remember good old days when VOAs were called VFD. Back in 1986, Goddard, Kent and Olive published a new construction of the Virasoro minimal models. And this was essentially the completion of the proof of unitarity for certain Virasoro minimal models. And so essentially what they did was it's called the Cosec construction, but what they did was they said, look, we can, in model language, take the tensor product, have an affine VOA for SL2 at level K, tensor it with the level 1 version of the same thing, and inside it, there's a diagonal embedding of the level K plus 1 affine VOA. Take the commutant of that sub-VOA, and lo and behold, you get the Virasoro minimal model. So this is very good. But you'll see here that this construction is only for the unitary minimal models, because you work out what the central charges corresponding to all of these constructions give you. Well, they give you precisely the unitary discrete series. And so Kent, who was a PhD student at the time, in his thesis, he said, well, it's a very natural question. Can you also get the non-unitary minimal models out of this? And at the time, physicists didn't really know what that meant, because there was a quantization condition on the level which says that for the physical theory to make sense as a string theory, the level has to be an integer, a non-negative integer. And so in order to make sense of this, we need to figure out how to generalize this. And if you want to get a non-unitary minimal model, which corresponds to having the Virasoro parameters being different by more than one, then you have to make sense of fractional levels. So here we've got, I guess this is actually, as you probably all know, the definition of the admissible levels for SL2, as pointed out by Katsumoto, introduced by them in and what we know is that at these levels, the sort of, if you like, classical category O for these vertex operator algebras happens to be semi-simple and finite, but it's not Q-finite. So it still looks like it might correspond to a rational VOA, but in fact, the Q-finiteness tells us immediately that it's not. Well, we still get some nice properties. So Katsumoto's work was basically looking at what happens to the characters under the modular transformations. And they're like, yes, we have vector-valued modular transformations, so everything should be good. But then almost immediately, people started connecting modular transformations with fusion coefficients. So everybody here knows the Valinda formula, which I've written out, assuming strong rationality. And the point is that these fusion coefficients, these n's on the left, have to be non-negative integers, but these s's are some weird algebraic numbers. And we know that this is true. This is great for sufficiently nice VOAs. But if you jump ahead to 1988, two physicists, Coe and Sorber, immediately sort of said, hey, let's just try and see whether this works for these admissible level SL2 theories. And it turns out that it nearly works. It just slightly fails. What happens is that when you compute these fusion coefficients using the S matrix that Katz and Mokumoto have derived for you, you end up that always, no matter which admissible level you choose, well, as long as it's not a non-negative integer, then you'll always get a few negative numbers. Right? They'll always be integers, but they won't be non-negative. The fusion coefficients can't be negative. It just doesn't make sense. So there's lots of work on this. And, essentially in physics, everybody sort of went, this is a real problem, but we don't really know how to fix it. So, the answer, of course, as Dražen and Anton had already pointed out back in 95, is that these theories aren't rational. And so we have to be a lot more careful. And so So Drazen and Anton had shown back in 95 that these affine VOAs admit infinitely many irreducible modules. So we'll discuss this in more detail shortly. But just to fill out the rest of the history, this classification result dates back to 95. And it's a natural question to ask, what do we do with all of these infinitely many irreducible modules? But one answer to this came shortly thereafter, where Fagan Semikatov and Dipunen noticed that the famous Kazama-Suzuki relation, which connects modules of, let's say, affine SL2 to modules of the n equals 2 superconformal minimal models. Well, this, when you look at it closely, this doesn't really work. If you want to get, say, a Verma module for the n equals 2 minimal models, you can't just start with a Verma module for LKSL2. You have to start with something a lot more general. And they call these things relaxed Verma modules. And so more generally, we get the notion of a relaxed highest weight module, which I will talk about shortly. They also added what are called spectral flows of these things to the mix. So essentially, in order for Kazama-Suzuki to work as an equivalence between categories of modules, then you have to start on the affine VOA side with relaxed highest weight modules and their spectral flows. All right, but from there, some famous papers from around 2000 or so. Moldacino and Naguri introduced the SL2R Wessamina-Witten model, which was, of course, quite physically interesting because, they say SL2R, but what they mean is the universal cover, which is sort of the unpacking of anti-de Sitter space in 3 dimensions. So they made a proposal for the spectrum, which essentially uses these relaxed highest weight modules and their spectral flows. The next year, Matthias Gabadeel looked in a more, let's say, mathematical way at a very specific example. So he took one of these fractional levels, k equals -4/3, and he chose this one because it has the fewest number of irreducible highest weight modules. So you'd think it would be the simplest. And he showed, using some rather complicated fusion calculations, that if you just take the highest weight category, so if you just take the analog of the BGG category O, then you can show that if you fuse together 2 modules in this category, what you end up with is no longer in this category. And so if you want to have something like a tensor category or even just closure under fusion, if you start with the highest weight modules, he showed that you have to include at least some of the relaxed highest weight modules. You have to include their spectral flows. And in fact, you also get new things, which have now come to be called logarithmic modules. All right. And there's also historically a bit of work done for k equals -1/2, which of course has strong relations to effective bosons theory. So lots of interest on many fronts. All right, so that's the ancient history. It's already chewed up a fair bit of time. So let me get on with the rank 1 story. If you have any questions, please feel free to ask at any point. All right, so I'm going to call a VOA logarithmic if it admits logarithmic modules. And all that means is that L0 has to act non-semi-simply. It's going to have some finite rank Jordan blocks, not rank 1, obviously. And I'm also going to use a terminology, which is a rank 1 logarithmic VOA is, I'm not going to try to define it explicitly, but our main example will be admissible level SL2. So rank 1 is sort of a bit like the rank of the corresponding VOA, corresponding Lie algebra. It's not exactly, but we'll get back to that later. All right, so there's lots of things which we can cover, and to be honest, 50 minutes is probably not enough to do it justice. So we're just going to skip over it fairly quickly, but I wanted to take the opportunity to try to define a few things in the sort of simplest case. Hopefully people understand SL2 fairly well, and therefore the corresponding VOA shouldn't be too impossible to get your head around. So we're going to talk about relaxed highest weight modules, spectral flows, these logarithmic modules, We'll talk briefly about what happens with modular transformations and the Linder formula, so particular fusion coefficients. And to touch base with, I think, what Dražan's going to mention tomorrow, we'll also talk very briefly about something called inverse quantum Hamiltonian reduction. I won't try to explain exactly what that is, because that would take quite a bit of time. I'll leave that to Dražan. And I also want to introduce this notion of a logarithmic Kashtan-Lustig correspondence, because that's something which is highly conjectural, but in principle extremely powerful. At least in certain examples, that can tell us quite a lot, which otherwise we would have no idea how to understand. All right, so that's the plan for these rank 1 theories related to SL2. So let's start with the Reich's highest weight module. So I don't know if these are your favorite generators of SL2 or not. I hope they are, E, F, and H. And the affine algebra, you all know, you tensor with polynomials and centrally extend. And these guys, so this affine algebra has what we might call a generalized triangular decomposition. So effectively, you have 0 modes, positive modes, and negative modes. And I'm splitting everything up here according to the power of t, right? So positive, 0, negative. That's really all that's going on here. And so if you like, we're grading the affine algebra by what will eventually be the eigenvalue of L0 under the Sugawara construction. Okay, so I want to define a relaxed highest weight vector for this affine algebra to just be a simultaneous eigenvalue of the 0 mode corresponding to H, so that's our Cartan generator, and of course the central element. And we want this vector to be annihilated by all the positive modes. So it stands to reason. Well, we're not insisting that it gets annihilated by the 0 mode corresponding to E, right? So normally a highest weight vector, you'd also insist that E0 annihilates it. Here we don't. And so that's why it's called a relaxed highest weight vector. We've relaxed that condition. And then the standard thing, if you want to talk about a relaxed highest weight module, it's just any module which is generated by a single relaxed highest weight vector. Okay, now once we know how this works for the affine algebra, we can restrict this to the affine VOAs. And of course, modules over an affine VOA, LKSL2, means the central element is just K times the identity, the level times the identity. All right, so I've drawn a few pictures at the bottom here, which are little cartoons just to get a sense for what type of things one can have in the relaxed sphere. So you can still have highest weight modules, right? Those are examples of relaxed modules. They just happen to be ones in which you have a relaxed highest weight vector, which is annihilated by E0. So it's a genuine highest weight vector. And you may have their conjugates as well, right? And so in that case, F0 would annihilate the generating vector, the relaxed highest weight vector. Okay, but you can also have cases in which you don't have any vector annihilated by E0 and F0, or F0, sorry. So this can happen, and we'll see shortly that it happens quite often. But what this means is that one can have a highest weight representation, and I just realized I've labeled them incorrectly according to how I've drawn my axes. So sorry, this should be my highest weight representation, and this should be the conjugate highest weight representation, whatever. You can also have a sort of a standard textbook representation, and here you sort of have its highest and conjugate highest at the same time. In fact, it's a self-conjugate representation. So particular, if you see my L0 eigenvalue is increasing as I'm going down. So you can think of this as being induced from a finite dimensional representation of SL2. This one should be a infinite dimensional highest weight SL2 rep, then induced. And this is induced from an infinite dimensional lowest weight representation. Okay, but the point I want to get across is that there are many, many more. There are these things which I'll just refer to as relaxed. And these guys, the top space does not have a highest weight vector or a lowest weight vector. But it is what we call a dense module for SL2. Okay, I said before that Dražan and Anton have classified the irreducibles relaxed highest weight modules. And so it turns out that if we stick with the highest weight or the conjugate highest weight, there's only finitely many of them up to isomorphism. And so this is, what initially led people to think that maybe we have some sort of rational vertex operator algebra for these fractional levels. But as was found in the classification, there's actually a continuous family of these relaxed highest weight, irreducible relaxed highest weight modules. And so, in fact, there is a finite number of one parameter families. Right? So these families are indexed by complex number. So that's one parameter, sort of one continuum, and then a finite number of those parameters. Right now, these families consist of modules which are generically irreducible. And what that means is that the parameter which tells you which member of the family you're dealing with are almost all, in a measure theoretic sense, values of that parameter. The corresponding representation is irreducible. But there will be some for which that is not the case. So they'll have some reducible relaxed highest weight modules as well. Okay.
David, can I ask a question just so I get the right sense of the word conjugate? Do you tend to mean it like conjugating by an element of the finite Weyl group, or more like a spectral flow translation?
In this case, what we're doing is we're twisting a highest weight representation by the non-trivial Weyl reflection of finite SL2.
Ah, okay.
Yeah. When we do SL3 a bit later on, it won't be an element of the Weyl group. It'll be the outer automorphism corresponding to the Dickinson.
Okay.
Well, it won't be exactly that. It'll be that multiplied by the longest element of the Weyl group. But it's an outer automorphism.
Right. Okay, thanks.
Yeah. It's the automorphism which acts as -1 on the carton. All right. So be that as it may, we have all of these relaxed highest weight modules, and we also have to talk very briefly about spectral flow because we want to build up a complete set of modules, right? So Dražen and Anton classified all of the irreducibles in the, let's call it the relaxed category of relaxed highest weight modules, or if you like, the category of positive energy modules or n-graded modules. But that turns out to be not enough in order to get all the nice results that we know and love for vertex operator algebra module categories. And so we're going to have to introduce spectral flow. So these are automorphisms of the affine algebra. And I've written down, what the definition is, but, you shouldn't really think of them like this. You should think of them as being sort of like generalizations of the translations of the affine Weyl group. So in fact, they're, so in the affine Weyl group proper, the translations form a lattice isomorphic to the co-root lattice. And so it turns out that in order to get an automorphism, you can extend that, generalize that slightly, replace the co-root lattice by what's called the co-weight lattice, still get automorphisms. Those are precisely the spectral flow automorphisms of an affine category. Right, and they're called spectral flow. This first arose in physics. People notice this for the n equals 2 superconformal minimal models. And physicists call this spectral flow because they do not preserve L naught. Right? So they don't preserve conformal weights, they change them. So the spectrum is changing. The fact that it's a flow is kind of a bit of a misnomer because this is discrete. So here L is just supposed to be an integer. All right, but if you've got some automorphisms of our affine algebra, you can check that these preserve the Cartan subalgebra, right? So H naught goes to a linear combination of H naught and K, and K goes to K. So we're preserving the Cartan subalgebra. And so what you can do is you can just take your representation, you can compose it with one of these automorphisms and get a new representation. We call that twisting by the spectral flow automorphism. And what you're going to get then is you're going to get invertible functors on any category which is closed under this twisting operation. And because we preserve the Cartan subalgebra, we know that the category of all weight modules over the affine VOA will be preserved in this way. All right, so this is basically telling us that the category we want to be looking at is the category of weight modules over our vertex operator algebra. Right? So this is a much smaller category than the category of all affine weight modules. Okay, but we can do that, and we can look at our little pictures. So even if we start with a nice picture where our irreducible is induced from a finite dimensional SL2 module, when you apply spectral flow, you might get something which is induced from a infinite dimensional highest weight SL2 module. But then when you spectral flow again, unless the level happens to be a non-negative integer, you end up with things which cannot be induced from any SL2 representation, at least not unless you change your triangular decomposition for the induction. And so what we have here then, if you remember the L0 eigenvalue was increasing as we go down, what we have here is we have a case where the eigenvalues of L0 conformal weights are not bounded below. So this extends off as far as you like. This is a little bit annoying and possibly scary if you're not used to it, but these are perfectly fine representations of the VOA, perfectly fine. And in fact, one of Slava's early results from 2001 with Silka, I'm not sure if I'm pronouncing that correctly, this result effectively tells you that if you take into account all of the spectral flows of the irreducibles that Dražen and Anton classified, then you get a complete set of irreducibles in the category of weight modules over our affine VOA. So that's nice. That means that if we understand the relaxed highest weight modules and we understand spectral flow, then we understand all the irreducibles of our weight category, and hopefully that will be enough in order to do nice things. Well, I've said before that some of our relaxed families have some reducible modules, non-semi-simple modules, and the way this can work is fairly easy to see when you're dealing with SL2, because you can draw nice pictures. And so here, I've drawn a picture where we have a highest weight module, which looks like this. So we have a highest weight vector here. Oops. And it turns out that there is always a corresponding conjugate highest weight module, which is on the right-hand side of my picture here. And you can connect the two by just declaring and checking that this is consistent with all the requirements to be a representation. You just declare that this highest weight vector is no longer a highest weight vector, and when you act on it with E0, you end up going to the conjugate highest weight vector over here. All right, but F0 doesn't take you back again. No. That's actually inconsistent. It's only a one-way thing. And so what we get then is we get a non-split extension of our highest weight module and our conjugate highest weight module. So this type of non-semi-simplicity comes for free, right? In your classification, you just notice that this can happen, and in fact, you then, with a bit of work, prove that it does happen. In fact, these are the simplest non-split extensions that you can come up with. You can get more complicated ones in general. This is sort of the base case. And these are the guys which sort of fill the gaps in these one-parameter families of relaxed highest weight modules. We have almost always irreducible modules, but for certain parameter choices, you'll end up with something which looks like this. All right, so we might describe the weight category for affine SL2 at these fractional levels K as being almost semi-simple. So what that means is that if we look at these families, then, as I said, almost all of them are irreducible, but it's even better than that, because not only are the irreducible ones irreducible, they also turn out to be projective and injective. That's relatively straightforward to check. So what we end up with is a description of the category, of the weight category, in terms of its blocks, right? So you decompose a category into blocks. We're going to get an uncountably infinite number of semi-simple blocks, right? And each one of them will have a single irreducible, and that will be projective and injective. So that's, basically what happens in rational theories. But the only difficulty comes about because there are also some non-semi-simple blocks where all the fun happens, and it turns out there are only a finite number of those, which is relatively cool. there's only finitely many things that you need to understand. So sometimes we call these blocks the semi-simple blocks and their modules typical, and the non-semi-simple blocks and the corresponding modules are called atypical, because this is how Katz described the case for Lie superalgebras back in the good old days. I'm also just going to use the term standard modules. So basically all elements of these one parameter families are going to be called standard modules. All right, so I've written at the end here, just for reference, the vacuum module of our affine VOA is always going to be atypical. It always belongs to one of these non-semi-simple blocks. That's kind of the way it has to be. Otherwise, we would not expect to have a logarithmic theory. Okay, so we want to understand these atypical blocks, right? The typical ones are easy. We want to understand the atypical ones. So I said earlier that not only are there these sort of extensions which I drew for you here, these guys are non-split extensions, but they're not sort of logarithmic in the sense that L0 acts non-semi-simply, right? L0 actually acts completely semi-simply on these non-split extensions. Right? These standard modules like this, we still have a semi-simple action of L0. Right? If we want a logarithmic VOA, we're supposed to have a non-semi-simple action of L0. And it turns out that, that these things always exist. So Matthias Gabadil constructed the first back in 2001. And I guess I can skip ahead. Drajan has a very nice general construction of these, which I won't talk about, but maybe he will. So we get these logarithmic modules for our affine VOA. And essentially what happens is you take any atypical module. So here I've taken a picture representing an atypical highest way irreducible. And what we essentially do here is we take its, I won't say what we do. It turns out that there is an injective hull, or if you prefer, take it at the top and then take the projective cover. So the fact that these exist is actually quite deep and difficult, but in fact they do. And so I've tried to draw it here in terms of a Lervi diagram, so socle at the bottom and head at the top. And over here I've tried to draw a cartoon, which is more like the pictures I was showing before. So you have two copies of your highest weight module, which are the socle and the head, and they overlap, of course, because they're the same module. And then we have a conjugate highest weight module, and we have a spectral flow of a highest weight module. And you put those all together and glue them in some nice way, for example, like this, where you see the explicit actions of E0, F0, F1, and E minus 1. That's just one way in which this can occur. It's not the only way. And you put them together and you get an indecomposable, and L0 acts with rank 2 Jordan blocks. Effectively what happens is that the highest weight module here in the head, when you act, say, on the generating vector here with L0, you'll end up with, well, the action gives you a Jordan block, and the Jordan partner, or the image, if you like, is the corresponding vector down in the socle. Right, so you get a rank 2 Jordan block connecting the head to the socle. All right, I did want to mention also that this category is, not only so nice. This weight category not only has projective covers and injective hulls and all the things that you might like, it also has tilting modules satisfying BGG reciprocity. And so I said before that we have these standard modules, which were the members of the one parameter family. So it's about as nice a category as you could expect on the sort of abelian front. And of course, we'll probably hear lots more about tensor categorical structure in other talks this week. But it's nice. That's kind of the point. All right. I want to spend a little bit of time talking about modularity, but it seems that I am taking more time than I was hoping. So let me not beat around the bush. So the problem with these, as we discussed before, the Verlinder formula doesn't work if we just stick with highest weight modules, the way one might naively think to start, right? And so category O is not modular in any sense of the word. The Verlinder formula doesn't work, right? But I claim that the weight category is modular, and it's modular, but in the sense that we have infinitely many irreducibles and non-semi-simple things galore, but nevertheless it is modular, right? So if you write down the characters of these standard modules, it turns out that these can be written in terms of distributions which are supported precisely at the poles of the highest weight characters. So that's a very interesting observation, and it allows you to make all sorts of connections between this and sort of analytic properties of distributions. And the standard modules have characters which turn out to form a basis for the space of all characters of our weight category, which is even better again. And but this basis is indexed by, well, it's a continuous, it's an uncountable basis, and so we have a continuous parameter corresponding to these families. And so when we want our modular group to act, we're not going to act on a character and return a linear combination of characters in the usual sense, right? Not a finite sum, not even an infinite sum of characters. We're going to have to integrate. And so when we talk about the S transform and the T transform, they're not going to return matrices so much as integral operators. So we can the generalization of the S matrix and the T matrix is then the kernel of the integral operator. And that sounds messy, but it's actually very simple, because you're just thinking now about something which is generalizing a Fourier transform, for example, a Laplace transform, if that be inclined. Right, the T operator for the weight category, you can work it out. It's diagonal and unitary, just like you'd expect for a rational CFT. The S operator, the kernel, turns out to be symmetric. It's also unitary. It's a quick calculation. And if you square it, you get precisely the conjugation matrix. So again, just like for rational VOAs, the only difference is now you've got a continuous parameter. And so buoyed by this success, you say, let's try the Verlinder formula, but now instead of having a sum over all my irreducibles, I'm going to have to integrate over them. You do so, and you end up with fusion coefficients, which are non-negative integers. Right? The Verlinder formula does work, but only if you work with the weight category. Right? And that's why I say that this is a modular category. Okay, the nice thing about this calculation is that when you do it, you find that precise agreement with the fusion rules, or the fusion coefficients, which were known for the two small values of the level, which were computed sort of arduously. There we go. Okay. Inverse reduction, I may kind of skip. I'll leave that for Dražen to describe in more detail. But suffice to say that this is an incredibly powerful and exciting collection of functors, which at least potentially has promises to allow us to do just about anything. So as a quick shout out, I've already said that Dražen was able to use these techniques in order to construct all the logarithmic modules for our SL2 VOAs at the permissible levels. So that's pretty exciting. One of the things which I'm not too sure about is how easy it is to extract all of the structure of the modules this way. You can construct them explicitly, but then analyzing these things is still a formidable task. I'll leave it to Dražen to decide how formidable that is. So I want to take a little bit of time to explain this thing called the Kashtan-Lustig correspondence. So there's a classical Kashtan-Lustig correspondence, and by classical I mean last century. But that's not what I'm talking about here. What I want to talk about here is essentially correspondence, categorical equivalences between VOA module category and a quantum group category. So, typically this will be a quantum group at some root of unity. And so, the affine VOAs that we get here, the LKSL2, I don't know of a direct correspondence with a quantum group category, although maybe there are ones. But essentially, if we look at the weight category for SL2, then there's a very close relation to the category of modules for its parafermionic coset, which is where you take commutant of the obvious Heisenberg, right, the one corresponding to the Cartan subalgebra inside the VOA. And so these guys are not exactly the same, but if you know one, you essentially know the other. So we're very close. It turns out that if we take these nice levels that we saw before, then this parafermionic coset turns out to be examples of what are called singlet vertex operator algebras. And it's these singlet vertex operator algebras which appear to have these Kashtan-Lustig correspondences. This is all conjectural, but it's pretty well tested in the case of SL2 that if you want to get a quantum group category which is the same, and you can choose what the same means, then the singlet VOAs do the job for you, and the quantum group turns out to be this funny thing called an unrolled restricted quantum group. I won't explain what that is either, because fortunately time is never my friend. Okay, but the upshot of this is that this unrolled restricted quantum group is much easier its category of modules is much easier to analyze. So it turns out that the weight category, which is the one you're interested in, has finite dimensional standard modules. So the Verma modules are the standard modules in that category. The irreducibles are finite dimensional, and you have finite dimensional projective covers. The quantum group itself is not finite dimensional. That's no, but all of the modules in the category are. So you can just do brute force calculations and figure out, what's my projective look like? Oh, it looks like this, and then use the Kashtan-Lustig correspondence to get some extremely non-trivial predictions about what is going to happen on the SL2 side, on the VOA side. Okay, well, seems Jethro, when should I finish?
Hello?
Yeah.
Well, I don't know. So we had said 50 minutes plus 10 minutes for questions, but take a few more minutes to get to the punchline.
Yeah. Look, I'll just kind of I shall be brief. The idea is just to outline. I've already told you basically how the story is going to work, and this was really just an excuse to sort of show what we've been doing for SL3. So, once again, we want to study certain affine VOAs at admissible level. So for SL3, admissibility looks like this. The same tools which I outlined before are going to come back and help us again. So we're looking for the weight category. We can understand it by classifying the relaxed size weight modules. And this was done by Arakawa, Futorny, Ramirez back in 2016 using Gelfand-Set and combinatorics. There are other ways to approach this now, of course. But this is what I call a rank 2 story, because effectively we have two different directions in which one can relax. So if you think the Cartan subalgebra for SL3 is two-dimensional, so instead of just having a one-dimensional picture for the top space, now you can have a two-dimensional picture. And so this means that you have three types of irreducible. You can have a sort of fully relaxed highest weight module, where the top space is dense, and that means in all root directions. You can have a sort of a semi-relaxed case in which you only have this denseness in one root direction, and then you can have just your standard highest weight modules. And so, if you think about the two directions as being our parameters, which they are, then the fully relaxed irreducibles form two parameter families, the semi-relaxed form one parameter families, and the highest weight modules are just a discrete family all by themselves. Okay. So again, once you've classified these, if you want a classification of all of the modules in the weight category, then you just have to apply spectral flow. And there are sort of two discrete directions of spectral flow because the co-weight lattice is rank 2 for SL3. So what happens is that, as with SL2, your relaxed family degenerates. So if you take a fully relaxed family, and so there's parameters, which this is a fundamental domain, but don't worry too much. You take the parameters, and if you tune the parameters just so, you'll hit one of these black lines. And the black lines, what happens is that you break up into some number of semi-relaxed families. So you end up with this sort of this middle family. And if you tune the parameters so that you end up at one of these blue dots, it breaks up further into highest weight modules. So, there's a nice way of understanding this, and you have to understand all of these degenerations and all of the spectral flow orbits so that you can understand how the category can qualify to be modular. All right, so there's still some technical difficulties, and I think it's very fair to say that this is work in progress, but just to outline where we are. Logarithmic modules. So I should say here, of course, we have these degenerations, and if we take our two-parameter family of fully relaxed modules and degenerate to a black or a blue point, then what we end up with are non-split extensions. So that's all well and good. We have that already, but we don't get logarithmic modules that way. And logarithmic modules were very recently constructed in a paper of Dražan, Thomas, and Naoki, and again using the inverse Hamiltonian reduction. And interestingly, they were able to construct modules in which the Jordan blocks for L0 had rank 3. All right, so for SL2, we only had rank 2, and for SL3, we now get rank 3. I don't believe that they were able to make any even conjectures for what the structures of these logarithmic modules would be, but we'll get to that shortly. In sort of, if you like, a companion paper, Kazuya and Simon and myself looked at a specific case where you take the level to be -3 halves. And so in that case, we were able to verify the modularity explicitly, which was rather nice. So the weight category turns out to be modular. We believe that this is going to be true in complete generality, but verifying it in more than just a few special cases still requires a fair bit of work. I think we have the ability to do that. But things are basically working as they have before. And I want to finish, if Jethro will give me another minute, by just saying that we can also employ a conjectural Kashtan-Lustig correspondence to get some more information about the case where the level is -3 halves. So I think this is really interesting. Once again, this correspondence doesn't work with the affine algebra itself. It works with the parafermionic coset. And because this parafermionic coset, as Dražan and Anton once again tell us, is a singlet algebra. So in fact, it's the SL3 generalization of the singlet algebra, particular parameter. So if you look down at the bottom in this diagram, here we have some very neat little unrolled restricted quantum group, right, where the representations are finite dimensional and you can figure them out. And then we have this conjectural correspondence to the singlet model, and then we can sort of invert the coset in order to recover the weight category for our affine VOA and try to understand what type of representations we get there, what sort of structures we see. And just out of interest, the singlet model has a simple current extension, which for SL2 would be the triplet model, but here is not the triplet model. It's sometimes called the octuplet model that Semi-Kartov studied about 10 years ago. All right, so what kind of structures can we get for our affine algebra? Well, I've drawn them out just to kind of scare you. So you get projective covers, which look very much like the SL2 ones, and this is what you get if you take the projective cover, one of these semi-relaxed irreducibles. These are sort of the middle irreducibles in the classification theorem. But if you take a highest weight module, one like this, called L, or the vacuum module, then you end up with different structures entirely. And these projective covers are much, much more complicated. So these are the Lervi diagrams, and they, I don't think you would guess those. At least I certainly wouldn't have guessed them. And I haven't tried to put in what all the stars are, but you can read the paper if you like, and see that they're all obtained, and they involve spectral flows, they involve twists by the automorphisms of SL3. So it's quite complicated. My purpose here, and I will finish by saying that what you can see from these projectives is that there is a good chance that this is consistent with the construction which resulted in rank 3 Jordan blocks. So you can see here, if you start from an S and you act with L0, you'll go from the head to the socle. So that will be a rank 2 Jordan block, presumably. But over here in this projective cover, we have our head L. There's an L halfway down the Lervi diagram, and then there's another L down here. So that's consistent with the possibility that there's a rank 3 Jordan block, which is, of course, exactly what was discovered with inverse Hamiltonian reduction. And the same thing for the vacuum module. You have the head here. You actually have 4 copies down here. You're kind of spoiled for choice. And then you have the socle as well. So rank 3 Jordan blocks. All right. So I have talked for far too long. I'm just going to shut up now. You can read that if you want. Otherwise, thank you so much for your patience. Very funny to see all of these hands moving on the screen and not being able to hear anything.
So are there any questions? Yep.
Hi, David. Thank you for the talk. I have a couple of questions. I want to confirm something. In your previous slide, you had... So these guys represent a class, a self-extension, say, of order 2 from S to S, and then of order 3, in the X3 from L to L. Is that...
It's not a self-extension, no. So, for example, over here I have 4 irreducibles, which are glued together, right? So the socle is irreducible, the head is irreducible, but then the second Lervi layer is the direct...
Yeah, so I wonder if it's an X2 class, not an X1, but a class in X2 from S to S, and then a class in X3, L to L.
Yes, maybe.
The picture, at least for the S to S guy, so this is exactly what happens for the triplet, right? And presumably this is what you can do some construction to get the triplet extension from that rhombus that I see here at the top.
Yeah, so this is the same type of pattern that we see for SL2 and also for the triplet, which is rank 1. So this is sort of the standard rank 1 picture for all non-semi-simple kind of categories. Yes. Yes, you can, I think, write this in terms of an X2. That's not the way I've ever kind of tried to think about it, but yes, probably.
So it would be very nice, at least for me, to understand if you can even conjecture that that you can construct always classes in Xn from a simple to the same simple. So
yeah, so I mean here all of these projective covers are self-dual, and this is easy to see on the quantum group side because we have the duality functor, and the irreducibles are all self-dual, so the projective covers are. Why should this be true at the VOA level? Yeah, I don't think I have a good answer to that. Maybe Kazuya has an answer. He's in the audience, I believe.
Right, thanks.
I don't know whether he wants to try to answer that, though.
I've got a quick one, another one, which is also a very loose question. In your modularity slide, so I wonder if you can guess something that separates boundary admissible levels from admissible levels in general. So do you see something different?
Yeah. Well, hang on, I'm just trying to find where my slide was. So, yeah, so we have, so we parameterize the level in terms of two integers. I think I did it over here for SL3, U and V. And it seems that V is kind of the most important for many respects. And of course, the boundary admissible case is when U is as small as possible. So essentially what happens is that U is kind of like the rational part and V is the non-rational part. So if I take U to be boundary admissible, the complexity gets reduced, but it's sort of the rational complexity. To try to be a little more precise, what kind of happens is that you have inside your category, you sort of have you have a subcategory of modules which look like they're at level U minus 3 in this case, right? So when you're at boundary admissible level, it looks like you're at level 0. You just have the vacuum module. And so that does simplify a lot of the work. Yeah, so I guess conjecturally we would say that that you have an embedding of fusion rings, for example. So the fusion ring at the rational level U minus 3 is embedded inside the fusion ring for the level for the level U over V, shifted level U over V. I don't know if that's helping though. Is that kind of the thing you were after? Or?
Yeah, just an intuition. Thank you.
Yeah, so it is simpler, but it's kind of simpler in a way which is less scary than what happens for V. So with V, there are sort of certain things which happen when V is very small, and then once V gets sufficiently large, all hell breaks loose. So the difference is between degenerate admissible and non-degenerate admissible. So in the case of SL3, the non-degenerate admissible cases correspond to V being at least 3. And so in that case, you end up with sort of maximal complexity. And in terms of inverse Hamiltonian reduction, you can sort of see how this relates with the nilpotent orbits, because if V is equal to 1, you have a rational affine VOA, at least if U is sufficiently large, right? We're talking admissible level. And so what you have then is that the zero nilpotent orbit is the interesting one. You already have rationality and everything is done. When V is equal to 2, you have the minimal nilpotent orbit sort of comes into the game, and you get added complexity based on that. And, but for V equals 2, the minimal W algebra is rational. So Tomoyuki proved that back in, I think, 2013 or so. And so in that case, if you're doing inverse Hamiltonian reduction to understand the SL3 theory, you start from the minimal W algebra, and then you invert the reduction in order to build up all of these logarithmic structures, this complication. Now, when V is at least 3, you have to start from the principal reduction or the regular reduction, which is the W3 algebra. And again, because it's a non-degenerate admissible level, that thing is rational. But then now you have sort of two steps to go to. You have to pass from the principal reduction up to the minimal reduction. So that's already adding you sort of 1 degree of complication. And then to get the next degree of complication, you have to pass from the minimal back to the affine case. So, you know, there's sort of there's more complexity in the value of V than there is in the value of U for that reason. Sorry, I'm probably just rambling now. It's all fun stuff.
Are there other questions? Okay, so if not, let's thank the speaker again.
Thank you very much, everybody.
Thank you. Right, so now we have a coffee break, and I think the biscuits have arrived already. We resume at 10:30.